The radial solutions for the hydrogen atom Schrodinger equation can be found by mathematical means, and they're related to the Laguerre polynomials, which is the result of another differential equation that has been solved in the distant past. I'm not going to go through and detail the solution of the equation, but I'll remind you that in fact what we're talking about is the solution to this particular differential equation, where I've filled in the values for the eigenvalues over here on the right hand side, and remind you that these can be written more simply as 1 over 2n squared times the energy, the Hartree energy. But this is basically the equation that we're talking about the solutions for. But what I want to deal with now are the actual eigenfunctions for this equation. Now I'm going to write this down, and I'm going to beg your indulgence because these functions look a little bit complicated, but we'll talk about ways that we can sort of simplify what they say. They're often written as negative sign in front because of the way the Laguerre polynomials are defined. They're defined as negative, so that means they're going to cancel out this negative. So don't worry about the negative sign too much. It's going to go away when we start talking about the real functions. There is a normalization factor. The normalization factor depends upon the quantum numbers n and l, but it may be less important for us to know exactly what that dependence is. Another piece of the normalization constant is given here, and I'm going to write it as 2z over n times a0, where once again this a0 is the Bohr radius, and this is raised to the 3/2. Now what is this z here? Well, I've inserted it over here as well, and you'll notice it's part of the Coulomb interaction. Well, even though hydrogen has just a single proton, we can also use the solutions for the hydrogen atom for example, the helium ion, He+, or the lithium diion, Li2+, in which case we have a nucleus that has more than one proton. And when this is the case, this Z will be greater than 1. So if you don't like the Z here, just replace it with a 1 in your head, but this would allow us to generalize our solutions to other types of systems. All right, so we have this 2z over na0 raised to the 3/2, and now we'll have a part that's dependent upon r. So r is here over na0, and this is now raised to the L power, L being the angular momentum quantum number. This is then multiplied by exponential decay that looks like this, zr over n times a0. You notice wherever we have r, we have a0 in the denominator. So in effect, r becomes dimensionless in these equations, except perhaps overall. But anyway, these prefactors here that depend upon r are then multiplied by something, and I'm going to use a script L to really distinguish it. And it has a couple of indices. One is subscript n plus L and a superscript 2L plus 1. And the arguments of these functions are again these 2zr over na0. All right, and these are the associated Laguerre polynomials. So let me write that out for you. Laguerre being another famous French mathematician. All right, so this overall equation basically indicates that we have r raised to the power of L, an exponential decay in r, and a polynomial in r. And I'll just mention that these polynomials are not too difficult for small values of n and L. They're typically have a highest order that is of order L. So let's take a look at a couple of examples. So let's first look at an example of n equals 1 and L has to equal 0 in this particular case. And so what we would have is a Laguerre polynomial, an associated Laguerre polynomial L11. N is equal to 1, L is equal to 0, so 1 plus 0 is 1. 2L plus 1 is 2 times 0 plus 1, that gives 1. So the Laguerre polynomial in this particular case is just equal to 1. All right, that makes things easy. Now we have our radial wave function, which we can write now as a normalization constant. times factor, and I'm going to just take z equal to 1 in this case, but there would be a z in the numerator for this particular term. So it would be 2 over n equals 1 times a0 raised to the 3/2. And then I'm going to have again the argument here of 2 times 1 times r, so that's just 2r, over n equals 1 times a0, that's just a0. And this is raised to the L power, which is 0. So in fact, this is just going to be equal to 1 also. And then we have e to the minus z, so e to the minus 1 times r divided by 1 times a0. So we'll end up with a expression like this, and we'll have the Laguerre polynomial of 1. So in fact, this whole thing ends up just being a constant, and I'll write that as a times e to the minus r over a0. Okay, all that work for that. All right, seems kind of crazy, but this in fact is the simplest of all the hydrogen atom wave functions. All right, if we went to say n equals 2 and L equals 0, then we'd have an associated Laguerre polynomial that would be indexed as follows. N plus L is 2 plus 0, so that's a 2 down here. 2L plus 1 is still 1. And it turns out that this Laguerre polynomial is just equal to minus 4 plus 2x. So now if I write out my wave function, my radial wave function, I would end up with something that looks like this. I'll have a constant, and I'm going to forego a lot of the extra work here. I'll have a constant, which is the normalization constant, plus this term, and I'll have 2 minus r over 2a0 times the exponential e to the minus r over 2a0. All right, so fairly tidy expression here for this second radial equation. Now, one thing I want to note about these functions, these radial wave functions, is that for the most part they do not equal to 0, but where they can equal 0 is when this part, when the associated Laguerre polynomial part can equal to 0. So this is where we're likely to get nodes come in. Now, I've written these things out painstakingly with R, but in fact it's a common practice to define, if you will, a scaled radial coordinate, and we can write that scaling factor as 2 times z, again assuming that z is not equal to 1, times r divided by n times a0. So if we use this as our operational coordinate for the radial wave function, we can now write these radial wave functions as follows. They're going to be some normalization constant, which I won't specify any further than that because I really want to focus on the functional dependence, but they'll be proportional to rho to the L, e to the minus rho over 2 times the associated Laguerre polynomial with an argument of rho. All right, so now this is a fairly simple looking expression. We've got rho raised to the L, which means that whenever we have L equals 0, this term goes away, doesn't just equals 1. We'll have a decaying exponential and a polynomial over on here. This polynomial, as I mentioned, has a limited order. I think I said L, but it's really a polynomial of order n minus L minus 1. All right, so limited extent. Okay, so this is the place where we're going to encounter nodes in the radial wave function. So I'll call those radial nodes, and we'll define them more precisely a little bit later on. But we've done all this work to get the radial function. It's worthwhile to point out that the total wave function for the hydrogen atom is this radial part times the angular part, and the angular part was simply the spherical harmonics. So now if I write this as we did when we did separation of variables, we'll have r sub nl, that is a function of r only, and the spherical harmonics that are functions of the two angles. And both of these parts are individually normalized, so the overall wave function is normalized. Now what I want you to notice about this is that these wave functions have three different labels. Those labels are n, l, and m. All right, and these are things that we'll associate ultimately with quantum numbers. But these three different labels are all we need to specify the overall wave function for the hydrogen atom. So in other words, when we write this overall wave function, we could write psi sub nlm of r, theta, and phi, and that would completely specify the spatial elements of this wave function. Now, we've seen what the radial part's like, we've seen what the spherical harmonics are like. It's now combining those two that presents our challenge, because if we want to visualize these wave functions, we're going to need to resort to some fairly special techniques and special approaches, and we'll talk about that in a subsequent video.